47? So it has a graph, is that right?
It asked us to go back to one. Yeah. That's why. We're in section 2.3.
No, I think. Yeah, I don't want to do tomorrow's, tonight's homework. 2.3, right? No, I think that. 47. Oh, draw the graph, okay, I got you. Of a continuous function. And so what we know is that f prime of x is greater than 0 for x less than -2. And that f prime of x is going to be less than 0 for -2 less than x less than +2. That f prime of x is equal to 0 for x greater than 2. And that has to be continuous. That's kind of important detail. So what we're getting now, they're trying to get us to think about what does it mean when the derivative is positive, negative, or 0. So we're going to go from -2 to +2. These are the places where interesting things happen. So if the derivative is positive, what does that mean about the graph? Does that make any sense what that's telling us?
Is it above the x-axis?
That would be if f was positive. If f of x was positive, the graph would be above the x-axis because all the y values would be positive. What if the derivative is positive?
Then it's always increasing.
That's what we get out of this. Did you catch that? If f is positive, then the function is increasing. If f is negative, the function is going to decrease. And what if the derivative is 0?
Then
It's going to stay horizontal. Now, we don't have any y values at all. So there's lots of different ways. Your graph doesn't have to look exactly like this. But up until we get to 2, it's going to need to be increasing. So we could do something like, say, up to -2, it's there. Then until we get to 2, it's going to be decreasing. So we could do something like that. And then for the rest of the way, it's got to be horizontal. Okay? Now, the way I connected these is optional because it didn't tell us anything about concavity. So you could, you could have made it look kind of weird, but these exotic functions, you could have made it increase this way and decrease this way. You could have even made them be like sharp corner points. Oh, what are the colors? So we could have done something like this, because it's not telling us anything about what's happening at those endpoints. That they could have been, something special that we'll talk about down the road. Okay? Anything else?
Can you do question 1?
Yeah, that's tough when you get stuck on one, isn't it? Not a good sign in general. So this is one where I think they're giving you a table of values, and they're asking you to approximate that prime of 2. And I don't think they give you anything specific. So you have on this table, so you've got 0 is going to be 10, 2 is going to be 18, and 4 is going to be 24. This is enough for us to do the first part of the question. So if we want to approximate f prime of 2, we can't find the exact derivative there. So we have a choice, and they don't really give you any direction, so you're free. So this kind of question has actually appeared on AP exams pretty regularly. Sometimes they'll give you more direction, like use, point to the right or point to the left or some other kind of direction. But with no direction at all, we're going to use an average rate of change to approximate the instantaneous rate of change. So we could use those 2 points and do 24 minus 18 over 4 minus 2, and that's going to be 6 divided by 2, which is 3. But you could also, since we didn't have direction, you could have used those 2 points and gone 18 minus 10 over 2 minus 0 and gotten 4. It's just an approximation. You could even have used the point on either side and gone 24 minus 10 over 4 minus 0 is 14 over 4 is going to be 7 halves. Any of those would be acceptable. Now, I'll try to get you in the habit of doing this now. These questions come up so regularly. I mean, you're almost guaranteed to see something like this on an AP exam. When they ask you to do that, you must show a difference and a quotient to get the point. You can't just write the answer down and do the arithmetic in your head, because that won't get the point. So you have to show a difference that you're subtracting something and a quotient that you're dividing by something. And you could do it, you could write it this way. You could do, f of 4 minus f of 2 over 4 minus 2. That would be acceptable as well. So you can either use the actual numbers or use it notationally, but you want to show it as a difference, that is a subtraction, and a quotient, a division. And then you go to your answer. So just try to build that into habit, because those are regularly occurring questions. What else?
Can we do 51?
I don't know, maybe. Let's see. So 51, using a graph, explain why g of x is an odd function, if g of x is an odd function, g prime is even. So these ideas of trying to get a graph of the derivatives from the function they're going to be around for a while. And we'll spend a lot of time looking at this in more and more detail as we start bringing in more and more complicated functions. Because right now we're pretty much dealing with polynomials, which behave very nicely. But we'll start bringing in other kinds of functions that don't behave as nicely. And then can we still figure out what to do with the derivative? Part of this is the even odd things. So we want an even function. What does it mean to be even? It's going to be symmetric with respect to the y-axis. Priya's speaking to me in sign language here, so I think I understood that correctly. So we can look at something, a familiar looking even function, like y equals x squared. So it has symmetry in the y-axis. Now let's see if we can try to figure out what the graph of its derivative is going to look like. So we know what jumps out at us is there's going to be a horizontal tangent right there. So that's going to be where the derivative, so this, I'm going to call like f of x. And then I'm going to do the f prime is going to be here. So this is going to be a 0, so I'm going to put the 0 there. Now these are going to be positive. But because of the symmetry, whatever positive value this has on the right side, this is going to be that same value but negative on the left. Does that make sense? And likewise, whatever slope that is here, the slope is going to be the same here, except it's going to be negative. So we're going to get this kind of, whatever this is doing, we're mirroring that in the negative side, which is going to make that be then symmetry in origin. And it's this idea that no matter what kind of even function you come up with, think of another favorite even function of ours, perhaps maybe suggesting a cosine curve, that you're going to get, again, whatever slopes you have on one side, you get the negative of that on the other side. And so you're going to get a lot of colors here. So, you have 0 here, so that's going to be a 0, and that looks maybe like a -1 there. So you're going to get something like this, and this looks like maybe a +1 there. And so you're going to get something maybe that looks like a sine curve or a negative sine curve. Okay. But again, the cosine curve is even because of the symmetry in the y-axis, and the sine curve is odd because you have symmetry in the origin. So it's a kind of a visual thing. What else? Okay, so how do we feel about taking derivatives using the power rule? Pretty solid? Yeah, not so good. So I'll try to build in a little bit of that review. We're going to talk here kind of about notation and interpretations of the derivative. So we're going to introduce some notations right off the bat, but I'll try to do some examples where we can maybe do some power rule derivative functions. So these are interpretations. Of the derivative. And then we're going to talk a lot about trying to figure out what the units are going to be when we take these kind of derivatives. Just like we saw last year, our book, I think, did a really nice job of trying to make us understand, what happens when you have an inverse, what are the units going to be when you look at an inverse, which you have to sometimes almost talk to yourself out loud. Well, that's going to be even more so now because we'll talk about derivatives of functions and derivatives of their inverse. Can we keep track of those units? So first, some notation. So there are a lot of different ways of representing a derivative. So one is, we could say f of x is equal to, say, 3x squared plus 5x plus 2. And then we could say its derivative, we use what is oftentimes referred to as either functional notation or they'll call it prime notation. So f prime indicates the derivative. And using our power rule, the derivative of 3x squared is going to be 6x. Are we okay with that? Good. And then the derivative of 5x is going to be 5. And the derivative of 2 is going to be 0. Now, sometimes we'll also use this notation. So we'll say y is equal to, we'll say maybe the square root of x plus 1 over x. And another way to denote a derivative is you'll see it oftentimes written as dy dx. And that's how we say that, is dy dx. Now, this is sometimes referred to as Leibniz notation, named after Leibniz, one of the co-creators of calculus with Newton. So Newton and Leibniz both kind of give credit for that. Historians say that Leibniz put a lot of time and thought into what he used for his symbolism, knowing that that could be helpful to help people understand what that was representing, or it could really be a roadblock. And I think none of Newton's notation survives. It was really cumbersome. When he talked about limits, he talked about fluxions and things. It was really, you had to kind of get into his head to kind of understand that. But what Leibniz was saying here is like, this is coming from delta y over delta x, right? We have seen that what we call the difference quotient, which is that change in y over the change in x. That's exactly our slope formula from our algebra 2 days, where we took y2 minus y1 over x2 minus x1. And so what Leibniz was trying to suggest is that as this denominator, as h or delta x goes to 0, then this goes from being that slope of a secant line, average rate of change, to the actual derivative, the instantaneous rate of change, the slope of the tangent line. So it became this dy dx coming from the delta y, delta x. So that's what that notation is supposed to suggest. And sometimes it's really nice in clarifying what exactly is that function and what exactly is the independent variable. Is it time? Is it x? Is it something else? Is it a radius? And so sometimes this can be very clarifying. And so we would say here dy dx. So here we're going to think of square root as 1/2. So using a power rule, its derivative is going to be 1/2 x to the negative 1/2. We okay with that? And the 1 over x, we're thinking of as x to the negative 1. So its derivative is going to be negative 1 comes in front. X to the, subtract 1 from the negative 1 is going to be negative 2. You okay with that? So there's some notation there. Now, alternatively, you'll see we talked about this a little bit. This derivative as an operator. So we can say something like d dx is how we would read that. And it means to differentiate or take the derivative of whatever follows in that bracket notation. So if we did something like maybe pi x plus e to the third, and we wanted to find its derivative, this notation, we could either write, say d dx of this, or differentiate this, or take the derivative of this. That's what that's implying, that you're going to do this operation of differentiating on whatever is inside that bracket. And so the derivative of pi times x is going to be the derivative of x is, our question 2, 1. And so pi times x will have a derivative that is pi. It's a constant times x. It's going to be just that coefficient, just that constant. And e to the third, its derivative is going to be it's not 3e to the second. It's 0 because e is a constant. And so the derivative of a constant is 0. So that is the derivative of that. Then other symbols too. So sometimes you'll see it written as df dx. Yeah, taking off from this this Leibniz notation idea that if you call your function f, then you might want to call it df dx. We will see a lot of particle motion where the s of t is going to be the motion of some particle along a line, either a horizontal or a vertical line. So if we got something like, 4t to the third minus 2t plus 7, this is the motion of some particle, then oftentimes that derivative will be denoted using Leibniz notation. So here again, you're getting clarification that we're taking the derivative of the s function with respect to the independent variable is t. And so then other than that, it's just a calculus problem. We're still just taking derivatives. And so the derivative of 4x to the third is going to be 12x squared. The derivative of a negative 2t is going to be negative 2, and the derivative of 7 is going to be 0. Okay? So that's just all notation. Now, units matter. So, we're trying to sort through what exactly these units are going to be. So typically, on a typical AP exam, there will be, 1 or 2 or maybe a few more, usually at least a couple, where they're going to ask you to indicate units. And so then they want to know, do you understand what the units are in this particular column? So typically those come up in like pre-response questions. So you have some big word problem and they'll ask you part A, part B, part C. Then maybe part D or part E will be indicate the units. Or it may be like we saw in the first one where we had the table of values and you're approximating that derivative at a point, they may say indicate the units. And so that'll typically be a point. It's not a huge deal, but sometimes we will see that keeping track of the units as the problems get more complicated, keeping track of the units can sometimes help you to know what exactly you should be doing. Should you take a derivative? Or we're going to learn, more, in January, when you take an integral, it's going to kind of go the reverse of taking a derivative. And so sometimes a question can be challenging to make, oh man, what should I be doing? Is it a derivative? Is it an integral? What do they want? And if you keep track of the units, that can oftentimes give you a clue as to what you should be doing in that problem. So it's worth the investment of effort, because they can be tough. So if we had, say, S of t, and that was, say, that the units were, say, S was in meters, and the t was in seconds, then the ds dt, that instantaneous rate of change of position, which is also known as what? What is the first derivative? What is it? It is velocity, so it's also velocity. But you can see it's going to be a change in s over a change in t. And since s is going to be in meters and t is in seconds, the units on this is going to be meters per second. Does that make sense? Okay, so which is a velocity measurement. Okay, which is velocity. Okay, so rate of change, now notice that is going to be the same units if it was an average rate of change. So an average rate of change would be a delta f. So now you're taking, the position at some particular time minus the position at a different time over the change in that time. That's like our y2 minus y1 over x2 minus x1. That's an average change. It's going to have the same units. So average rate of change and instantaneous rate of change are always going to have the same units. So that's not going to be a reliable clue as to whether you should be differentiating or approximating it or whatever. Okay, so when we say also that, so when they ask for a rate of change, if they don't say an average rate of change, that's understood now in this class to mean instantaneous rate of change. So let's see how much we can muddle the waters here. So the cost, we will say, of building a house with capital A square feet is given by some function C of A. So the cost of whatever that square foot of that house is. And we're going to assume here that, so we know the A is given in square feet, and we'll just say C is going to be in dollars. So not hundreds of dollars or thousands of dollars, but just in dollars. So what does, see if we can find our way through this, what does C prime of A, which could also be written in Leibniz notation as dCdA, what does that represent? Do we want to take a stab at that, or do we need some help? Yeah, Taylor.
Dollars per square foot.
So those are going to be the units, is dollars per square foot. So what exactly does that mean, though? Can you put into words what that means? So what does dCdA mean? What does C prime of A mean? Give it some context here. So one thing that we'll see, and it's early on in the game, a derivative is always a rate of change. It's a rate of change. So it's the rate of change of the cost per square foot. So if this is a positive number, which I think would have to be, then it's going to be what's that cost per square foot? So let me give you an example, I'm gonna give you an example with numbers in it, yeah, and we'll see how we can tease that out a little bit more. So if we write C prime of 2,000, so there's one notation for that, using the prime notation. Now, another way of writing that in Leibniz notation is a little more awkward. It's going to be written this way. So the Leibniz notation, it has some advantages in terms of kind of understanding where these things are, what they mean. It's the change in cost per change in area. But evaluating it, this is way nicer than this. This is just kind of an awkward way to do it, but that's how it's going to be done. So if I say that is equal to 100, now let's see what this means. This in the language of, I guess, economists or business people, this will be, they call the derivative here, it's a derivative of the cost function. They would call that marginal cost. So a businessman or a business major or an economist, they would say, oh, the derivative of the cost, you're talking about the marginal cost. So what they interpret this now to mean, what this interpretation is, you want to take a stab at it, or? So it's a rate of change of cost per square foot. Okay, in an AP exam, that would get you full credit. It's the rate of change. You have to call the rate of change of the cost per square foot in area when you have, what's this 2,000 represent? So when you already have a house that's 2,000 square feet, then what they would say, the cost of building the next square foot is going to be $100. So the idea is that this rate of change in cost. So this would be, let me say that. So the cost of building one more square foot when 2,000 square feet have been built is $100. It's a rate of change. So the idea is when you first build a house, there's going to be, a lot of expenses up front. You got to dig, you got to lay the foundation, all that stuff. But once you have a house of a certain size, adding another square foot or a few more square feet is not going to be as expensive as the initial build. And so it's changing. The rate of change of the cost per square foot is changing. It's a function of the square feet. It would be big, and then we expect it to go down. It would decrease as you add more. And if you've already built your palace of 10,000 square feet, adding another square foot, it's not going to be all that much because you've already made the big investment. Okay, so let's see if we get any better at this. It's tough. So we will say that the cost of extracting capital T tons of coal is, the cost C is equal to F of capital T. And can we try a stab at what does F prime of 1,000 equal 50 mean? So our cost function now is for extracting tons of coal. So what does F prime of 1,000 equal 50 represent? But you turn to your neighbor and tell them what you think. Ainsley, want to take a shot? What do you think?
Oh, we said, the cost of extracting 1 more ton of coal after extracting 1,000 tons of coal is 50.
So in general, I mean, the units, so let's talk units too. So the units here, what you said was great. I wouldn't change any of that. So the units here would be what? So it's going to be so we would call this, another way of naming this would be the change in C over the change in capital T. So your units are going to be these units per this unit. So it would be dollars per ton. So this is a $50 per ton is what that is. The rate of change of the cost in dollars per ton. But the way it would be, this is a marginal cost too. So the way it would be used in a business setting is exactly what Ainsley said. That after you've extracted 1,000 tons, the cost of extracting that 1,000 first ton of coal is going to be $50. Okay, it's more likely that you would not get this kind of a question on an AP exam. This would be more like if you were in a business calculus class. That's how they would talk about that. But that's fine. I'm going to turn around the other way. I'm going to give you a rate of change. Can you figure out how to write it as a derivative? Okay, so water flows through a pipe at a constant rate of 10 cubic feet per second. 10 cubic feet per second. Interpret this rate as a derivative of a function, of some function. And your clue is going to be the units. So the clue is going to be the units there. So what kind of, first let's do that. So how can we write that as a derivative? Can anybody give me something in Leibniz notation that would be this, looking at those units there? So you have cubic feet, and you got seconds. Cubic feet's got to come from where? If your units are cubic feet, where's that coming from? It's a volume, right. And then the seconds is a time. So cubic feet per second in Leibniz notation is going to be a dV dt. Does that make sense? Or, and I think that would be the better way, probably the more clear way of doing it. Or you could say d prime of t, where you're showing that it's a derivative with the prime notation and showing that the independent variable is a t by writing it that way. Does that make sense? Okay, so we would say then, you could say dv dt is equal to 10. So now we've expressed that as a derivative. Okay, now we're going to get to the nitty-gritty here. You thought these were tough last year in AP Prep. Now we've added a whole other layer to it. So we're going to say let capital N equals G of T be the estimated number of electric cars in use, number of electric cars in use in the US in thousands T years after 1995. Explain the meaning of, we're trying to work our way from confidence builder to kind of soul crushing difficult. You'll get that pretty quick. We'll progress pretty quick. So first is G of 4 is equal to 1, I think that's a 32. Second one is going to be G prime of 5 is equal to 36. Third one is going to be G inverse of 670 is equal to 4. Then you might get some PTSD from those, and this one on last year. And you thought that was tough. Now we're going to have, catch this, G inverse prime of 670 is equal to 0.0137. Cool. All right. We're trying to get into the flow of things. We're going to use our units in our explanation here. So you can turn to your neighbor, build a little confidence, and explain what does G of 4 equal 132 mean. This is going to be a test question about this time of year in AP Prep last year. I don't know if you remember the rabbit question. I just did that. Oh, I'm hearing good answers here. You ready? What you got, McPherson?
I have the first one.
That's what I want, the first one.
In 1999, the number of electric cars was 132,000.
Something comparable to that? Okay, so 4 years after 1995, in 1999, there were 132,000 electric cars in use in the U.S. Nice. Okay. Let's do a little calculus. You can turn to your neighbor and talk about what does G prime of 5 equals 36 and include units in that discussion. Alan, you want to give it a shot? That was a rhetorical question.
And we found that after, in 2000, the rate of the cars.
The rate of change of
cars is 36,000.
It's a rate.
Cars,
So that's be something per something.
36,000 cars per year.
There you go. So you could say the rate of change of the number of cars on the road in the U.S. in the year 2000 was 36,000 per year. Or you could also add, another way of saying this, because this is positive, is the number of cars increasing or decreasing? It's going up because it's positive. So the rate of growth, or the rate of change is growing, or you can even say just the rate of growth of electric cars in the U.S. is 36,000 per year. But you have to include the word rate in there, so make sure that's clear. Rate of change is important. Oh, Here comes our dreaded inverse. It's stand on your head when you do these to get to think of it right. Now the input value is what the old output value was. So think about what you're inputting and what you're getting out, and how to say that in a coherent sentence. Go ahead, discuss.
Yeah, so now you have
That sounds pretty good. Thomas, what do you think?
In 1999, there were 670,000 electric cars in the U.S.
And if you want to say more kind of the way it is, so
Okay.
what you said is fine.
There were
So you say the number of cars, electric cars in the U.S. will reach 670,000 4 years after 95, in 1999. So this is kind of what, this is the input and that leads to this. So the U.S. will end up getting 670,000 cars on the road in 1999. Okay. How you do calculus with an inverse? Give it a shot.
So it's oh wait.
rate of change.
Keep track of units. Keep track of units. So what units are you inputting here?
Cars.
Thousands of cars. And what are you outputting?
Yes.
Yes. Now you know, what is that? Okay, what are we inputting onto the original function? So what are we outputting on the inverse? Okay, so it's going to be a rate of change in, this is weird, years per car. The change in years per car. So this is how many years it will take to get another electric car on the road when we reach 670,000 cars. It is complicated. So it's like saying, you know, you're mapping this, here's the car growth. So you get to 670,000. How much time is it going to take to sell that 670,000 and first car? That many years. Okay, so it's a rate of change in years per car. It is tough. It is tough. So think of units. So we input years, we get out thousands of cars. We're inputting thousands of cars. We're outputting time in years. And now we're doing a rate of change in years per car. How many years per car is it going to take to increase the number of cars on the road? Yeah. So when we've sold, we have 670,000 cars on the road. It's still increasing. How long is it going to take to get the next car on the road? Just many years.
So like after
The Heisenberg.
670,000 cars,
Years to get that next 670,000 first car on the road. So I mean, we had them that
I
long.
was so I'll probably feel about it, but like I had bad reactions and I was like, what might be sick?
Just what we would begin trying to say. If you feel that you're allergic to these,
Sounds good.
oh, yes, yes.
Also, I think I'm gonna come in after school tomorrow because I'm confused. So I might be here.
Can I come after school today? Oh, yeah. Can't find that.